currently visiting the Institute for Advanced Study, who will speak about interesting open problems and closed problems involving groups. As usual, if you'd like to join us for dinner, as usual place, Evelyn at 6:45. Please let me know immediately after the talk. Thank you.
Thank you for the invitation. I will tell you about problems in groups, which I think have some aspects of experimental mathematics. I hope so. I hope that maybe someone here will have ideas regarding this. So let's start with a theorem of Fourier from 51, which is the following. In the alternating group, every element is a commutator. Commutator. So in commutator we mean the commutator of two elements is the element x1, x minus 1, y minus 1, which is, this is trivial if and only if the two elements commute. And he showed combinatorially that every element in the alternating group is a commutator of two permutations. And you can take conjecture that this is true for every simple, finite, simple group. So when this conjecture was made, there was nothing close to the classification of finite simple groups. Today we know, I think, most people believe in the classification. We know all the finite simple groups, so we can tackle this group by one group at a time, but at that point it was a general conjecture about simple group, and I think mostly because this is the simplest example for a simple group, so why not the conjecture that it holds for all group? And he also states it very mildly. He said maybe it could be nice if this happens for all finite simple groups.
So it was a question, maybe, not a conjecture.
He said it's possible that this happens for all finite simple group, but we are far from tackling this problem, something like this. And it became a theorem. So I think Liebeck, Shalev, Ryan, and Pierre. In 2010, they gave a proof. So, as usual in these cases, many specific cases were done before them, but they solved the remaining cases, and this relies heavily on the classification of finite simple groups. So at the end, it was reduced to several infinite families of simple groups.
So it was a case by case.
So it's case by case, but it's an infinite family. So you can't really check all the groups. You need to come with an argument, and a basic argument goes back to work of Frobenius. So in 1896, characters. So I'll tell you a little about characters. I don't want to assume that everybody knows what characters are, and then I'll explain how they relate to this problem and its proof. So so here's what Frobenius discovered. For a group G with R conjugacy classes, there exist R functions, all of them from G to the complex number. These are the characters. They're irreducible characters of G. Oh, so if I put this down, you won't see this?
Yeah, you have to start this one.
You can bring it down, but you can't move the other one up.
Okay, so I'll put it like this. So we have our function, the same number as the conjugacy classes. And what are they? Okay, first of all, they come from homomorphisms from the group to matrix groups over the complex. So for a homomorphism, if I have a homomorphism to a matrix group, it gives me a character which is, for every group element of the group, the trace of the corresponding element in the matrix. So first of all, this means that they are class functions. This means that conjugation doesn't change them because this is the trace of the conjugated function. So this is the trace of row A, row G, row H minus 1, and trace is invariant to conjugate. So it means that there is a chi of G. So characters are constant on conjugacy classes, and chi 1 to chi n reducible characters form an orthonormal basis to all class functions. So first of all, they span. First of all, you see that the number is okay. I mean, this would R was the number of conjugacy classes. We have here R characters, so it corresponds to the dimension. But moreover, they're linearly independent, which is not trivial. And furthermore, they are orthonormal with respect to the to this inner product. So it's the inner product of going over all the elements of the group. This is the standard inner product you take over a complex number, but you normalize it by G. Then it's then this is an orthonormal basis, meaning that this is 1 or 0, according to whether this is the same character or not. And so, two examples. One is...
Use the other board.
Oh, should I start with this? So one example is the cyclic group. Then chi I is the character which takes the number j to omega n to the ij, where omega n is the n roots of unity. And this means that if I write the numbers of the group, and these are the characters, so it makes sense to number them from 0 to n minus 1. As you see, this is the number of conjugacy classes because this is an abelian group, so every element is alone in its conjugacy class. We get here the standard van der Waals matrix of the n roots of unity. So this is one example, and you know that these are orthonormal and they span all the functions on the group. Now every function is a class function, and in general, if you have a function and any function on the group and you build it as a sum of these characters, so this is just the coefficient of this character in F. You say that this is the Fourier transform. f, these coefficients are the Fourier transform of the function. So in general, what characters gives you is the analog of Fourier transform for non-abelian groups. So this is for the cyclic group, and this extends nicely to all abelian, finite abelian groups. And when you go to a non-abelian group, you still have a very similar theory. So let's take this simplest non-abelian group, S3. Now we have the following. So the conjugacy classes are the one which correspond to the trivial permutation, to transposition, and cyclic shift. So we have the trivial character, which corresponds to the homomorphism, which takes all the elements to 1. We have this character, which correspond to the sign homomorphism, which take a permutation to the sign as a matrix in GL1C. And the interesting guy is obtained by looking at the action of a permutation on the vector space consisting of triples with sum through 0. So this is a vector space of dimension 2. We have 3 entries and 1 linear condition. And permutation preserved this, so this gives me an action of the group on a 2-dimensional space. And the trace of these actions give me the character, the third character, which is 2, 0, 1. And I mean, do it as an exercise if you've never seen it. It's not hard, but I won't show it. And actually, you can also write the matrices. So there is a choice of basis, but for one reasonable choice of basis, you get.
Are you sure? But it's not a second one.
Yeah.
The numbers are wrong.
I'll get to it in a minute.
Oh.
Good question. So with respect to some basis, you get omega 3 bar, and for that guy 1, 1. So you see this is 0 and this is minus 1. So it should be done. Okay, good thing that we did that. So this solves your problem?
Oh yeah, we just waited. Yeah.
Okay. So how does orthogonality looks here? Look at the product of this. So we have 1 plus 1 minus 1. So this is not 0, but you need to remember that here we have 3 elements. Also 1, 3, and 2, 3. And here we have 2 elements. 1, 2, 3, and 1, 3, 2. So this is 1 plus 1 3 times minus.
Well, you put the minus 1 on the wrong.
No, it was.
That one was fine. The minus
That
one
was
was
fine.
fine. The third entry in
So now
Chi
it's 1
3.
minus 3
No, it's plus 1. 1 minus 1, 1.
minus
Yeah, Chi 2 is right. Except it was before. So change the minus 1 to 1.
No, that's okay.
The first person was okay.
That's the sign.
Yeah.
Oh, this is this guy. Okay.
Yeah.
So 2, yeah, okay. 2 is the trace of the identity matrix. So this one gives me this character. So this is 2, 0, and minus 1.
Yeah.
Okay. So now it just makes sense. So let's check. This is 2, here 0, and here minus 2. Okay. So they're orthogonal, and they span the class functions. Now this is a basis for the class function on S3. How does this relate to our story? So let's look at the counting function. So I count for every element the number of times it's obtained as a commutator. So this is the number of pairs xy in G such that xy is G. So this is a class function. If I look at n xy of some conjugation, it's the same because if some xy, if the commutator of some xy is g, then the commutator of hx, h minus 1, hy, h minus 1 is hg, h minus 1. So it means that for any solution to x commutator y equal g corresponds a solution to commutator something something equal g conjugated by h. Which means that we can write a Fourier decomposition, which means that we can write the counting function as a sum over all the characters, the Fourier coefficient times the character. And this is what we're asking about. We have a word now, the word is the commutator, and we got numerical invariants for it. So what I mean by a word, I mean that now for any word you take, look at the x to the third, y minus 2, x2, z to the 5, I can ask, so let's call this word w, and I can define nw of g, which is the number of, now it will be x, y, z, such that w, when I substitute, so this is x, y, z in the group, the number of substitution will give me the element g. So for any word, I have a counting function, and all the counting functions are class functions by the same argument. And for any word, I have the Fourier coefficients of the word. So here's something strange. So Frobenius in 1896 showed that the Fourier coefficient of the commutator word is the following. The size of the group over the chi of 1. Now, if you remember that chi of 1 is the trace of, we have some homomorphism in the background of 1, and this is a trace of the identity matrix. So this is the dimension of the representation. The representation goes to GLN, so this is the n from the GLN. So usually this is written as the dimension of the character. The dimension of the character is the dimension of the GLN it came from. And okay, so several things happen here. First of all, this is universal. For any group G, we have the coefficients. Another thing is the following. So this is a theorem, I think, also of Frobenius, which is that the dimension of a character divides the size of the group. So this is, I think it's from the same year. It's not trivial. It sounds like one of the theorems that, some size of a subgroup divides the size of a group, something like this. It sounds like, okay, it should be very easy or not true, but it's neither. It's true and difficult. So this is something usually shown in the first course on characters or representations, but it's not, I challenge you to try to do it if you've never seen a proof. It's pretty hard. And it means that, this means that the Fourier coefficients are themselves natural numbers. This means that, okay, so this won't be clear for if you're not familiar with characters, but this means that the counting function itself is a character, meaning that it's a trace of some homomorphism to some matrix group, which is a very weird result because we don't know what is this homomorphism. So here's an open question, one open question, first open question for today. Which representation gives the character which counts the number of solution to xy and commutator y equals g? And this is, I think, this question appears a lot of times, and many people understood, saw that this is weird. We have this proof there is some representation gives in the character. We don't know which representation. If you can show this even for a single group, single family or group, it would be interesting.
But for the symmetric group, it's
Yeah,
not
for the
alone.
symmet- yeah, no.
It's even open for the symmetric group?
Yes, yes, it's very, I think it's very weird. Okay, so
The proof is only existence. It's not algorithmic.
it goes through some number theory, some properties of algebraic numbers. So it's somehow you use the fact that algebraic numbers are a ring, and the proof there is not constructive. So it's weird. Okay, so and another thing that it gives you is a solution for not a solution, but a direction to tackle the OR problem, the one I just erased. So we wanted to have this function strictly bigger than 0. This was our goal. So this is Orer's conjecture. And that for any element, the number of times obtained as a commutator is greater than 0. And by Frobenius, this is going over the character, then G over I of 1, and the value of G. So, and now we can split it to the trivial character. We always have the trivial character, which is the trivial homomorphism, sending all the group elements to 1. Then this is 1, and this is 1, so we get G. And we get the sum over all the non-trivial characters of G over chi 1, chi G. So basically, what you need to show is that this is not too small, negatively small. We have here G, we want it to be positive, so we just need to show that this doesn't take us too far, and this is what they do in the work. Eventually, everything is analysis of the representation theory of linear groups, a lot of algebraic geometry, and they can understand the dimensions of the representation and the values of the representation. But everything starts from an observation from the 19th century, which has very, very little theory following it. So there are very, very few words which we can say something about. So for these words, continue something like that, we have a formula. So we found the formula for these words, for the coefficient. So if we look at the Fourier coefficient of iterated commutators, then we found the formula for these in 2013, and then we discovered that someone already did it in 2011. But think about that, from 1896, it was left untouched for more than 100 years, but then it was done before us.
You mean you can write that as a commutator?
So I'll tell you what we get at the end. So I'll do it for 2.
So a different approach or different proofs?
It's what from
It's the same
Frobenius?
proof. The two.
No,
different
we have
proofs.
totally different proof. Ours is much better.
They're still publishable.
Yeah. No, and we have some consequence which they didn't have, so we managed to convince it's interesting. But we had something more general, but this was the nicest application.
Excuse me, and about the and, I guess it's true only for simple groups, because for a Gili is definitely not true. The n is 0.
Well, yeah. Yeah, simple groups, yes, they don't mean the ZP, not the cyclic prime groups. Yeah, somehow they're simple, but they're not part of the game. Everything is different there. Okay, so what do you get here? Okay, let's leave this for a moment. I wanted to show you how to compute things before we get to more. The reason I thought this could be interesting for experimental math seminar is that there are very few examples. So, okay, it's very easy to start playing with these things, and I think nobody really did it seriously. So I want to show you how you compute these things. And so this is GAP. I don't know if people are used to working in GAP. GAP is it's a very useful open source package for working with groups, and if you know Sage, then Sage use gaps for all the group theory parts. So I'm constructing here the symmetric group on 3 elements. Now I'm taking the conjugacy classes of the group and go over the conjugacy classes. To each one apply the function representatives. It's giving me representatives for the conjugacy classes. These are the same one we have here. Now I create just a list of zeros. I want to count how many times an object is obtained as a commutator. So I do for x in G, for y in G. I compute the commutator. I look for the position in the list of representative of conjugacy classes. If it fails, it means that it's not one of these representatives. I don't care about it. If it doesn't fail, I got one of these representatives, so I put +1 in the corresponding location, and I got this counting function. Now I turn it to a class function. I just tell that the type of the object is a class function, and I got a class function whose values are 18, 0, and 9. So we got here n xy is 18, 0, and 9. It means that the identity is obtained 18 times as a commutator, transposition never, which makes sense because this is an odd permutation and the commutator would always be even, and each one of these is obtained 9 times. So in total we have 36, which is 6 squared. It makes sense. And to compute the Fourier coefficient is also very easy. For every irreducible character, so C now goes over the reducible characters. For each one of them, I compute the scalar product of the character with the function, and I also tell me the values of the class function. So I get here each one of the characters and the corresponding Fourier coefficient. So you see 636 exactly corresponds to Frobenius. You remember it was G over times 1. This is exactly what we see here. 6 over 1, 6 over 2 is 3, 6 over 1 is 6. So basically what I'm saying is it's very easy to compute these values. And very little is known. Once you start, you can plot now any word you want and see weird phenomena. And very little is known. So I want to tell you some other things which are known. I'll get to the iterated commutators. Before that, Frobenius and Schul, I said that nothing happened between that result and the 21st century. That's not completely true. They did work on the nth power. So what they did there is showing that the Fourier coefficient of the word x to the n are integer. That's it. So again, in terms of representation, it means that the counting function here is not a character of representation, but it's a difference of representations. And they also understand completely what happens to x squared. For x squared, there is a good understanding what value it takes. But for the general xn, only I think that it's integers. So at that point you think, okay, until now everything was integer. Maybe the value for the Fourier values are always integers. So now you really need to go to the computer and try to find one which is not. And the simplest example that I think there is this word. So x squared, y squared, x, y minus 1. And the group is ESL 211. So these are matrices 2 by 2 over the field of 11 elements with determinant 1, and P means that we divide by the scalar matrices. So here we have, for some character, we have some character gives us Fourier coefficient